All right, ladies and gentlemen, welcome. We are about to walk through how to write a recursive and explicit function given a table. Now remember, at any point you can pause this video, you can go back and rewatch sections, or you can ask clarifying questions if what I said doesn't make sense. So let's dive right in. Let's say you're given this input-output table and you're asked to write a recursive and explicit function. First, we need to figure out what the pattern is here. How are our inputs increasing? Now, the first way I would test is to figure out, are they adding by the same number? And an easy way to figure that out is you take your second number, 12, and you subtract your first number, 7, to find what adds to get to 12. And 12 minus 7 is 5, which means 7 plus 5 is 12. Now let's test that out and see if it works to get to 17. 12 plus 5 is 17. So yes, it does work. And if we were going to continue the pattern, 17 plus 5 would get us 22. That would be our fourth term. Now, let's say we're going, that number is called our common difference. Our common difference is 5, positive 5. It increases by 5. Now, the other thing we need to know is what our initial value is. What's that number when x is 0? Where does our sequence begin? And if we add 5 to go forward, then going backward, we would have to subtract 5. 7 minus 5 is 2, so our initial value is 2. And from there, we can actually write a recursive function. All right, our recursive function has two parts. First, it has our starting value. What's our function when x is 0? Or what's our output when x is 0? You look over here, we actually wrote that down here, 2. We got it from the table here. Our y value is 2 when x is 0. That's our initial. Now, we're going to write our function, f of n, for any number. And I know that this notation means, and I'm going to put a little bracket to show what it means take the last, sorry, let me write that a different way. Take the previous term, the term before. That's why we have the n minus 1. Take the term before, and how does this pattern increase? Add 5, add 5, add 5, add 5. So we're going to take the term before and add 5. And that's going to give us our sequence. So if we took 2 and plugged it in here, we'd add 5, we get 7. If we take that answer, 7, and add 5, we get 12. If we took that answer and added 5, we get the next term. So that's our recursive function. It has two parts. Now, let's actually continue our table here. I'm going to create a whole nother column and a whole nother, it's going to show our common difference and initial value. So let's start with our initial value, 2. So I'm going to write that here, 2. And you say, well, if my pattern increases by 5, then if I start at 2, I'd had to add 5 to get to 7. 2 plus 5 is 7. Now, if I brought that down, 2 plus 5 is 7, and I ask, what did I do to get to 12? Well, I added 5. What about the next term to get to 17? 2 plus 5 plus 5 plus 5. And what about for 22? 2 plus 5. Now, take a guess. How many 5s am I going to write down for the fourth term? 4, right? Now, is there a way to simplify what we've just written? Is there a way to write this quicker? 2 plus 5 4 times. And indeed there is. 2 plus 5 4 times. 2 plus 5 times 4. Okay, so now I'm gonna figure out whether I can write this. Sorry about that. Whether I can write this for the third term. 2 plus 5. Now, how many 5s did I have here? 1, 2, 3. 2 plus 5 times 3. And the term before that, 2 plus 5 times 2. And I think you see the pattern here, 2 plus 5 times 1. And if you really wanted to go back, how many 5s did I add here? 0, right? So it works for every single term. And now we're able to write this for x. All right, so let's add a row down here. Let's see, if I have to write this for x to get any term, I would say, well, what's common about all of these equations? 2 plus 5, 2 plus 5 3 times, 2 plus 5 2 times, 2 plus 5 1 time, 2 plus 5. So my equation must have 2 plus 5, right? Times something. Now, I look here and I say, well, on the fourth term, it was 4 5s. On the third term, it was 3 5s. On the second term, it was 2 5s. So on the xth term, it must be x number of 5s. Whatever x value you have, that's how many 5s you're adding up. And indeed, that is called your explicit function. Your explicit function would read y equals 2 plus 5x. And the last thing you need to know is whether this is a geometric or arithmetic sequence. Now remember, geometric increases by multiplying by a number over and over, but ours adds a number over and over. So we can say that this is an arithmetic sequence with an initial value of 2 and a common difference of 5. There you have it.